Hello viewers, welcome back to my channel. Hope you are doing great. If you haven't subscribed to my channel yet, please go ahead and subscribe. I have created a bunch of playlists to cover various categories of the problem such as binary trees, graphs, linked lists, stacks, queues, dynamic programming, BFS, DFS and so on. Please check them out. I have uploaded the code for this problem to the GitHub repository. You can get the link from the description below this video. Let's jump into today's problem. Pseudo-palindromic paths in a binary tree. Given a binary tree where node values are digits from 1 to 9. A path in a binary tree is said to be pseudo-palindromic if at least one permutations of the node values in the path is a palindrome. Return the number of pseudo-palindromic paths going from root node to the leaf nodes. So basically we are given with a binary tree, and binary tree, right? So I'll just put in a abbreviated form. We are given with a binary tree and values are 1 to 9. So the node values in binary tree are 1 to 9 only, right? And a path in the binary tree is said to be pseudo-palindromic if at least one permutation of the node values in the path is palindrome. So basically what we are saying is the path itself may not be a palindrome, but any permutation of the path is a palindrome. Then we are saying that as a pseudo-palindromic, right? So we need to find out how many of such pseudo-palindromic paths are there from root to leaf. So we will have to see how many pseudo-palindromic paths are there in a given binary tree from root to leaf, right? So what is pseudo-palindromic, right? So pseudo-palindromic is saying if at least one permutation of the node values in the path is a palindrome, right? So for example, if you go through the example 1, right? So root to leaf paths. So that's what we need to remember, root node to leaf path. So 2, 3, 3, right? So the path is 2, 3, 3. So is this a palindrome, right? So 2, 3, 3. So it itself 2, 3, 3. So let's write next to each other, right? So 2, 3, 3. Is it a palindrome? No. But any permutation, so at least one permutation, right? So that means we can say any permutation of 2, 3, 3 is a palindrome. Then we will say 2, 3, 3 is a palindrome. So try to arrange 2, 3, 3 in a way that it can get to palindrome. So let's say 3 to 3. So 2, 3, 3 and 3 to 3. What we just did is put this 3 as the front, right? So that became 3 to 3. So this is a palindrome, right? This is a palindrome. So what we will say is 2, 3, 3 is pseudo-palindrome, right? Pseudo-palindrome. That's what we will say, right? So this is what we will say. Let me copy this and write. Right? So pseudo-palindromic. So 2, 3, 3 is pseudo-palindromic because if you just arrange 2, 3, 3 as 3, 2, 3, it became a palindrome. So that's what we have to find out. So the arrangement, what we are saying is the permutation, right? So we take whatever the numbers that are forming through the root to leaf and arrange in some order, some permutation order. And if that permutation is a palindrome, then we are good. That is what is the question that we need to solve. So let's try to understand what is the relation between this palindrome and permutation and pseudo-palindrome, right? So what is a palindrome? So palindrome is nothing but, so if you read left to right, so palindrome, right? So read left to right, right? And right to left. So they will be same. So it will result same. So that is a palindrome, right? So you read from left to right or right to left. For example, So if you read 233, 233, that is from left to right. From right to left, it will be 332, right? So but 233 and 2332 are not equal. So 233 itself is not a palindrome, right? So that's what we said. But when we arrange 233 as 323, so if you read from left to right or right to left, both of them are palindromes, right? So that's the reason why we are saying 233 is a pseudo palindrome, but 323 is palindrome. So but what we are interested in pseudo palindromes, not the palindromes as such, right? So we are interested in only pseudo palindromes. So pseudo palindrome is, it doesn't need to be reading from left to right or left to right resulting in the same, but any permutation of that. So now coming back to the permutation, right? Permutation, right? So what is the permutation? So you are given with a set of characters, in this case set of numbers, you arrange in whatever the order, right? It doesn't matter. So for 2, 3, 3, right? So let's take a better example, 1, 2, 3, right? So what are the permutations for 1, 2, 3? 1, 2, 3 is a permutation, 1, 3, 2 is a permutation, 2, 3, 1 is a permutation, 2, 1, 3 is a permutation, right? So 3, 1, 2 is a permutation, 3, 2, 1 is a permutation. So these are all, several different permutations are possible. But are any of these permutations are palindromes for 1, 2, 3? No, right? So none of them are palindromes. But in case of 2, 3, 3, let's go back to the 2, 3, 3 and come up with the permutations, right? So permutations, 2, 3, 3 is a permutation, right? 2, 3, 3. And 3, 2, 3 is a permutation, 3, 3, 2 is a permutation, right? What else? I think that's it, right? 2, 3, 3 is a permutation, 3, 2, 3 is a permutation, 3, 3, 2 is a permutation. That's it. So these are all the permutations. But of these permutations, any of them is a palindrome or not? Obviously 2, 3, 3 is not a palindrome. 3, 3, 2 is also not a palindrome. 3, 2, 3, yes, 3, 2, 3, 3, 2, 3. That is a palindrome. That's what we are interested. So we will say 2, 3, 3 is a pseudo palindrome. I hope the concept is clear. So let's move on, right? So now that we know what is a palindrome, what is a permutation, and so on, right? So let's try to identify when a string becomes a palindrome, right? So when we have to read from left to right and right to left, it should be same. What does it mean, right? So the length of a string can be even or odd, right? So if the length of the string is even, let's say, right? So that means if you read from left to right or right to left, all of them should be occurring even number of times. Let's say 1 to 2, 1, right? The length of the string is even and 1 occurred even number of times, 2 also occurred even number of times. So this is a palindrome, right? So when the length of the string is even and all the characters in the given string occurs even number of times, then we can make that string as palindrome, right? So that's an example, 1 to 2, 1, right? But so in this case, all characters should occur even number of times, even number of times. That's when the string length is even. What is odd? So, right, this is a palindrome, right? Palindrome. What does it mean? All characters except one character should occur even number of times. So that means all characters except one should occur even number of times. That remaining one character should occur obviously odd number of times, right? Remaining one character should occur odd number of times, right? So that's what is our hypothesis, odd number of times, right? So now with all this information, we are going to come up with an algorithm, right? So now the approach we are going to use here is Dfs, Depth-First Search. So since the given data structure is a binary tree, right? The binary tree, we are going to go with the Dfs approach, and we will use this thing, the information on the length of the string and even number of characters and odd number of characters in the given string, right? So since we have to come up with the root to leaf path, so now the steps in the Dfs are like this, right? So first get root to leaf path, right? And get counts of each character, each number, right? Get counts of each number. So how many times each number occurred. So if the length of the path is even, we need to see if all the characters occurred even number of times or not. If the length of the path is odd, all characters should occur even number of times except one. The remaining one character should occur odd number of times. That's what it is. So get the counts of each number, right? And then get the length of the path. With these three information, we can say, right, whether the path from leaf to root is, or root to leaf is a pseudo-palindromic or not. So what we are saying is, get the root to leaf path and get the length of the path. If it is even, we check whether all the number of characters are occurred even number of times, or all the number of characters occurred except one odd number of times. So this is one approach, right? Approach 1 we will say. So there is approach 2, right? So this is approach 2. So this one approach 1. So both of them are sort of Dfs only, right? In this approach 2, what we are going to do is, are we really need to calculate the length of the path here? All we care about these characters, right? So once we create a map of the number of characters and check if all of them are even, or if only one of them is odd and the rest of them are even, we are good, right? We actually don't need the length of the path. So all we need is, we create a map of character number and its count, right? Number and its count. So basically for 2, 3, 3, the map will be 2 occurred one time and 3 occurred 2 times, right? So that's what it is. So this is our map for 2, 3, 3, right? So 2, 3, 3 map is this one, right? Let's go down. Yeah, 2, 3, 3 map is this one. So 2 occurred one time and 3 occurred 2 times. So now we have this map, and let's apply this rule, right? So all characters should occur even number of times, but here this occurred even, but this occurred odd. But the next thing is, all characters except one should occur even number of times. So this occurred odd number, so this is just 1, and all should occur even number of times. All is, this is only 1. So that means for 2, 3, 3 we can create a palindrome, right? That means 2, 3, 3 will be a pseudo-palindrome. So what we are saying is, we have minimized, or we are not actually considering the length of the string anymore. All we are doing is, we are going through the path and preparing this map, right? We are going through the path and preparing this map. So when we are at the leaf node, we check the map. If the map has all even number of times, or except one, all of them are even number of times. That's it. Those two conditions if you check, we will say it is a pseudo-palindrome. So that is what we are going to look at as a first function. So let's go look at the first function. So this is palindrome. We are passed with a map, right? Excuse me. We are passed with a map. So in this map, if the map has only one character, let's say, right? Obviously single character is a palindrome, right? If there is no characters, that is also a palindrome. Otherwise, next we'll go through the map and try to see how many odd values are there, right? How many odd values, odd counts basically, not as so 3 is an odd value, 3 is an odd value, no, not that. Odd counts, right? How many odd counts are there? If the odd count is more than 1, we will return false then and there itself. Let's say if there is a path called 1, 2, 3, right? If there is a path called 1, 2, 3, what will be the map for this? 1 occurred one time, right? 2 occurred one time, 3 occurred one time, right? So all of them occurred odd number of times. So this cannot make a palindrome and this cannot make a pseudo-palindrome. So if odd occurs more than once, we will say immediately, okay, it is not a palindrome. That's what we are going to say. Odd number should occur only, odd number of counts should occur only once, right? So this is what is determining whether it is a palindrome or not. And then, so as we said, we are going to follow the Dfs approach and we create the map while going through the Dfs, right? Depth-First Search. So let's go ahead and look at the implementation for the Depth-First Search. So here I have created a map, right? Map will have number and the occurrences, right? So integer and integer, and we are keeping track of the pseudo-palindromic paths initialized to 0. So what we are going to do is a DFS and pass the root node to the DFS, and when whatever the count that we have accumulated in the pseudo-palindromic, we return at the end. So all the logic is there in the DFS, and the isPalindromic function that we have seen, we will be using that as part of the DFS, right? So now let's go. So DFS, we are passed with a node. If the node itself is null, we just return. We don't have to do anything. So for example, if the tree is null or empty, right, we will say, okay, it's a pseudo-palindromic. It is a null basically. So there are 0 pseudo-palindromic paths, right? Because there are number of nodes is 0, right? So otherwise, that means the tree itself is not null and that has a value. So we check if the map has corresponding value in the map. Current node value is there in the map. If not, we will increment. So basically, to start with, the map is empty. When we are at the root node, we add the 2 into the map and increment the 2. The occurrences of 2 is 1. So that's what we are doing here. And check if the node, the current is a leaf node or not. How can we check if it is a leaf node or not? Leaf node means it doesn't have a left subtree and it doesn't have a right subtree, right? So that's what we are checking. So this is essentially checking for leaf node, right? Check if it's a leaf node, right? So only for leaf nodes, both conditions are true, right? Leaf node doesn't have a left subtree and it doesn't have a right subtree. That means we have completed one root to leaf path. So check if the map can form a palindrome. If so, we just update the pseudo-palindromic to increment basically. We just increment the pseudo-palindromic. Otherwise, what we do is recursively call the left subtree and right subtree into the DFS, right? So that's what we are calling recursively. And finally, the recursion is over, right? What we are going to do is we will be decrementing the current value and removing the current value if the count is 0, right? Why are we doing this? This we are doing because when we are changing from left subtree to right subtree, we don't want to keep track of the old values anymore, right? So when we have traversed the whole left subtree here and we move to right subtree, we don't want to keep track of 3 occurred 2 times and 1 occurred 1 time. So that's why we are removing the older values once we go through the complete cycle of recursion, right? So that's what we are doing. So finally, whatever the value that we accumulated in the pseudo-palindromic, right, while doing the depth-first search of the given binary tree, we will be returning, right? So that's what it is. So if you observe, this is where isPalindromic we are using, right? So we are using there. So Now going back to try to get the time complexity and space complexity for this particular algorithm, right? So what is the time complexity taken for this, right? And what is the space complexity? So time complexity, so this is the main function, right? So DFS and pseudo-palindromic. So DFS, we need to go to the DFS. So we are visiting every node once, right, in the DFS. So that means if the binary tree has n nodes, let's say, so let's say binary tree has n nodes, right? So n nodes in binary tree. So the time required is order of n for doing the DFS, right? And in each DFS, when there is a leaf node, we are doing an extra calculation. What is that? Is palindrome. So is palindrome is a call which we are doing for every leaf node, right? So how many leaf nodes are there in a given binary tree? We don't know that, right? So if the number of nodes is n, right, and we need to get one more also. What is that? The maximum level, max level in binary tree is equal to h, let's say, right? So if the maximum level in the binary tree is h, then 2 power h nodes are there in leaf nodes. So leaf node count is leaf node count, right, is equal to 2 power h, right? Leaf node count is 2 power h. So how many times we are using this is palindrome function? 2 power h times, right? Because for every leaf node we need 2 power h leaf nodes are there, maximum, right, coming down, right? So is palindrome, how much time it is going to take? The map will have 1 to 9, right? That means 9. So this will be taking order of 9, that's it, right? So that will be executing order of 9 into order of 9. That means it's a constant. So left, this is not a leaf node count actually, this is a leaf node count, right, 2 power h into order of 9. So order of 9 is a constant. So that means what we will say is it will take 2 power h count. So the total time complexity will be order of n plus some constant into order of 2 power h, right? So since we don't know how many leaf nodes are there in the particular node, right? So what we will say is order of n minus 2 power h. So total complexity, what we will say is order of n minus 2 power h, right, 2 power h plus 2 power h into 2 power, so 2 power h into order of 9, right, into order of 9. So this is the total time complexity, right? What is the space complexity that we are going to use? We are using a map and we are using a pseudo-palindromic. So these are the two things that we are using, right? So pseudo-palindromic, since it is just an integer variable, we will say it is a constant space, right, for that. And for map, how many things we are using? Again, we will come back to 1 to 9, right? So map will be using a constant space, right? There are only 9 integers, so that is order of 9, right? So this is constant space, right? So this algorithm is overall, we will say order of n time complexity and the time complexity and space complexity is constant space for this particular algorithm. If you have any further questions, please post them in the comment section below. I will get back to you as soon as I can. I have posted the code for this particular problem to the GitHub repository in 2 languages, C# and Java. You can find the corresponding links in the description below this video. If you haven't subscribed to my channel yet, please go ahead and subscribe and share among your friends as much as you can. Please click on the bell icon so that you will be notified about my future videos. Thank you for watching. I will be back with another problem very soon. Till then, stay safe. Goodbye.